Like, no one's allowed being up without him, even if we're not doing anything interesting, like writing papers. But he's just really scared that somebody's going to have a party and he's not invited. That's a really good question, Keitsia. I'm thinking about it. The answer is yes, I will. I will post a couple of old finals. What will be the ratio of after midterm stuff to before midterm stuff on the exam? Oh, Melitza, it sounds like you think I'm thinking about that. I'm not. It'll be, I'd say roughly 70-30, 65-35 post-midterm to pre-midterm. That's not so much because I put more value on the post-midterm stuff than the pre-midterm stuff. It's more that we've scaffolded concepts the whole way through. And so a lot of the pre-midterm stuff, I can only ask a very simple question. The post-midterm stuff, I can ask you a question that asks you to draw on the pre-midterm stuff. So I can evaluate, I know you guys hate this, but I can evaluate the way you think through complex multi-step issues where you have to consider multiple factors. Because that's what a university education is all about. There is no naming on the exam. There will be a sign RNS. There is no naming on the exam. I have decided that it is a waste of everybody's time. Okay, so I've got Madison's questions and I've got Gabriella's questions, and we've got a hand up from Melissa and Chloe. I have no idea who's first, so I will address Gabriella's question first because it is easy. I have a general question. I hope this makes sense. When given starting material and as produced mechanism of products, what are key signs that the reaction will not occur? I think if the only possible mechanisms are impossible, that's a key sign. So what the hell do I mean by what I just said? So let's say the only possible mechanism would occur by forming a carbocation, but the only carbocation that could be formed would be a primary carbocation. Nothing happens. On one of the assignments, there was a question where there was an acidic hydrogen, there was an alcohol, and there was a base. The question said one equivalent of base, draw the product, and then a water workup. Well, one equivalent of base, strong base, is going to deprotonate alcohol, make an O-. And in that case, the O- could do nothing else. There was nothing else for it to do. And so it sat there until somebody added water back in and put the proton back on. So in that case, a reaction did occur. It was an acid-base reaction. But once you generated the charged species, it had no reactivity. There was nothing it could do. So I think those are the two main examples. Either when a reaction, the only mechanism available to the reaction is an impossible mechanism. So for example, if I gave you, as an example of that, if I said, this. Okay, we got a tertiary leaving group, but it's cold, and we're under basic conditions. So no carbocation possible. But cyanide is not a base, so it can't do an E2, so it can only do an SN2, but the only SN2 is on a tertiary leaving group. So we can eliminate eliminations, we can eliminate eliminations, and we can eliminate the substitutions, because the SN1 is not possible because you're basic and it's cold, and the SN2 is not possible because it's a tertiary leaving group, and it's tertiary leaving groups and SN2s don't mix. So in this case, you would have no reaction because all the possible reactions are impossible. Victoria, that's a very fast question, so I'll quickly take that. And then I'm going to come back to the raised hands then. Madison, your question is more complicated. I will get to it, but we'll go through some other stuff first. So Victoria, do you want to run through your SciComm idea?
Yeah, so are you familiar with The Office at all?
Like the television show?
Yes, yeah.
Yes.
Okay, there's a TikTok sound that is talking about where Michael is like wants to fire somebody, and so he's like, I want to get rid of this guy, and the HR person is like, Michael, you can't just get rid of somebody because you need cause, and he's like, I do have cause. It is because I hate them. So I was
Okay.
thinking of doing, is it called thalidium or thalidomide? That
Yeah.
drug that was used in the 1950s, and the S enantiomer is a pterogen or a teratogen or whatever,
Yeah.
and the R enantiomer is used today for treating other medications or
Yeah.
treating other symptoms. So I was thinking of having both of like the R and the S together, and the S is basically saying to like the scientist or the researcher, or the R is saying to the researcher, can I get rid of this guy? And the researcher's like, you can't get rid of him. You need this to get rid of him. And then the R is like, oh, I do have cause. It is because I hate him. I don't know if I just explained that really terribly. As I think I
I
did.
think it's going to be better as a visual joke. Yeah, and I think you're going to put this in kind of like a meme form, right? Or are you going to do?
I was gonna make a TikTok.
I think that can work. So you're going to like do an
Okay.
animated TikTok with this.
Yes.
That
Yeah.
I think will work a lot better in a video form than by
Mhm.
describing the joke. But I
Okay.
see your joke. I like your joke. It's a good joke. Um,
Okay.
just as a comment on this, where it's a good idea. One of the challenges, though, right, is thalidomide is weird because yes, there's an R and an S enantiomer. The problem is the
Hmm.
R and the S enantiomer interconvert in the body, so you can't. And it's kind of that's not normal for an enantiomer
Hmm.
to interconvert, but it does racemize in the body. So that's why we can't even now give it to pregnant women, because even if you make one enantio pure, it will convert to the other one and turn into a teratogen, which is awful because it's really good for controlling nausea. So
Oh,
if you're not
okay.
pregnant, it's a great drug. If you are pregnant, please don't take it. But I'll still like that. That's a minor detail. I still think you have a good basis for your joke.
Okay, so when I say like when the scientist like, oh, you can't get rid of it without doing this, like I had done some research on it, and it says you can get rid of it using, or I guess kind of partially get rid of it if you're saying that it interconverts in the body, by using high performance liquid chromatography.
Yep. So you can
And
separate enantiomers that way, and so you can get them
okay,
pure. The problem is they do interconvert slowly in the body. I don't know how quickly, but
okay,
any interconversion is enough where I go, yeah, I'm not giving that to you. Like, luckily I'm not a physician, so I don't need to prescribe drugs, but I
okay,
feel comfortable with it. But yeah, that's run with it because your theory is really good
okay,
and
and
it's fun.
that's enough information. I just want to make sure, like, because
I
I
think
want to
so.
make.
What you could also do is you could put like write a short, and this is for anyone who's doing something kind of creative like this, that's
Mm-hmm.
slightly abstract. Is you can write a really short paragraph saying, okay, here's a reference or two. This is the kind of the underlying concept,
Okay,
um,
perfect.
and sort of submit that, and you can submit a link to the TikTok on that. So what you submit is kind of a Word file with this just description and a link to the TikTok.
Okay, perfect. Okay, thank you so much.
Yeah, that works well. Okay, cool. Uh, okay, so let's. Um, I'm going to go with the people who get fewer questions. So Chloe.
Hi, Dr. Trant. How are you?
Hey, I'm good. How are
Uh,
you?
Good. I just had a question regarding the first midterm. It
Yeah,
was question 12. I'm going to paste the answer key in the chat if that's okay with you.
absolutely.
Okay. Just let me know if you see it. I just posted it.
Just waiting. It takes a second to come up, I think. Got it.
Okay, perfect. So my question regarding this was they selected the right chair conformation to be more stable, correct? I
Yes.
was just wondering, when comparing the axial to equatorial, in the first the first chair conformation, I selected that one to be more stable just because there was 2 equatorial to 1 axial. And I was wondering, would you compare the ratio between them, or you would compare the A values, like what would take priority?
The A values take priority, and so it's the sum of the A values. And so in
Okay.
this case, like a bromine and a carbonyl are pretty small, and isopropyl is big.
Right.
So the A value really dominates on the isopropyl.
Okay, that answers my question for that one. I was just.
I think
yeah.
I am going to agree that this is a challenging one. Yeah.
Okay, yeah, that was the one that when the regrading went out, it went down. So I was just curious based off like they didn't really explain like the ratio, which one would take priority.
It's because the A value is so much greater for the isopropyl.
Okay, perfect. I just had another quick question. Sorry.
Yeah.
So for question 13 with the scorpion question.
Yes.
When drawing the Newman projection, the biggest groups go anti from each other, correct?
Absolutely.
Right. And then you wrote in the answer key, if this is not in this form, then -1 marks. So my Newman projection was correct, but I just didn't have the biggest groups anti from each other. But if you rotate the front carbon, it would be correct. So I received 2 out of 4 on that question. So I was wondering if that was.
If everything was drawn, do you have your answer post? No,
I have my answer. I can put it into the chat. It's just gonna be one.
And you didn't like lose a carbon or something.
I don't think so. I'm going to I'll post in the chat right now.
Well, okay, sure. I'll take a look and then I'll try and pull this up and check. It's possible. I think the GAs were at times with that question a little bit harsh.
I have the answer as well. I can post in the chat if that helps you out.
I just found it. I just found my own copy of the answer key.
Okay, perfect.
Just give me a second. It's right at the end. So you posted yours. 1, 2. Yeah, because you unfolded it directly and just left it just like, yeah. Send me an email. You're going to get +1.
Okay, thank you. Yeah, I appreciate that.
No, absolutely. That you're just, yeah.
Okay, I have.
And just send me an email with it, like with the PowerPoint thingy, and I'll forward it, and the mark will be up.
No problem. I had another question. I don't know if you want to go with other people first and then come back to me. I'm willing to wait. It's another question off the midterm as well.
Okay, well, how would I walk through some other people? So Victoria, the same thing happened to you with the scorpion question? If that's the case, then yeah. So if you got the answer right and you lost, like you got the answer kind of right, in the same way, then you should have only lost 1 mark. And so please send me that correction using the format requested, and you will get your mark back because you deserve it.
Okay, thank you for going over that. I'll let other people ask their questions first, and then I'll come back later. Thank you.
I don't know. So I think we have Melitza, who has a question in both the chat and has her hand up. So I guess we're going next.
I have a question of just what's on the screen for no reaction. So when you wrote that initially, I thought that because it's tertiary, we wouldn't have SN2 occurring, but eventually SN1 could occur. How would we, like, I know there was an example we did in class where, like, there wasn't, like, a distinction with, like, the temperature, but I just didn't know that temperature played a part in substitution.
Definitely plays a part in making carbocations because you need a lot of energy to make a carbocation. And I will note that eventually you will get an SN1 reaction. I agree. I think at 0 degrees with sodium cyanide and that reagent, for 50% conversion at high concentration, I think we're probably looking on the order of about 500 years, which is, I agree, eventually. But that's a long time. So I think in general on a final exam, I'm not going to be asking no reaction questions like this. But I think if I was sort of saying explain what reaction you think would occur here, and that would be a fair question. I think what you could say is, look, I think the only thing that could happen would be an SN1. I do realize this is cold, so it's going to be slow. So I'm going to go with SN1, and you would get full marks. But you'd also get full marks. You said no reaction because it would be really slow because it's cold and your basic conditions. So an SN1 is not favored, so I don't think anything can happen. So I think I would give full marks to both of those answers because they're both correct technically. And I think I will avoid asking a question like this.
Okay, yeah, because I know in carbonyls, like heat can play a role in determining if a reaction will happen or not, but I didn't know that it stops substitutions from happening.
So I think what it does is heat. I think it's maybe I'm trying to simplify. So I sort of say heat stops the reaction from happening. Heat allows a reaction to happen in a reasonable amount of time. And so if you don't have heat, like if you leave a carboxylic acid with lithium aluminum hydride in a really sealed container at 0 degrees for like a year, you will reduce the carboxylic acid. But if you heat it, it'll go in about 20 minutes. So a year is not a reasonable length of time to wait for a reaction to occur. So I would say it's no reaction.
Okay. And then my second follow-up question on this is, what's the importance of the temperature in substitutions? Like, what does 0 degrees mean? And does it mean that like SN1 and SN2 won't happen? Or
it makes an SN1 less likely. So carbocation formation requires a lot of energy. So generally, higher temperatures are required to make carbocations. So if you have a system where you could potentially have either sort of an SN2E2 or an SN1E1, and one of them is hot. And so what I would probably ask is often sort of a comparison. One is hotter than another. I would expect the hotter reaction to lead to more SN1E1 like products, and the colder one to lead to more SN2E2 like products. Because heat allows for carbocation formation. Like that's a really high level intermediate because they're really unstable.
Okay. Is it required, like if we were doing like a synthesis and we were putting the reagents down and we wanted to do a SN1 and we put like, I don't know, like some like a weak base, would we then have to also put heat down?
No, I give it to you without heat.
Oh, okay.
Yeah.
Okay.
Because I think what I need to do to be absolutely clear on a question, you're allowed a little bit of vagueness because that would still be correct. It would take a long time, but it would still technically go. And often on a retrosynthesis question like that, what I'm really testing is more like the way you're thinking about the strategy of this. Which, congrats by the way, you seem to be a natural at it. Compared to what specific reagents you're using. That's not as important as long as they're, a reagent that would do it. So I don't care about specific conditions. I don't ask you to put a solvent down either, for example.
Okay. Okay, yeah. That's perfect. Because I didn't know, like, should I be putting these things down or not?
It never hurts, but you don't need to.
Okay. Okay. All right, I'll let someone else go.
Okay, Alyssa.
Hey, okay, I just had a few quick questions. On assignment 3, 4B.
Okay. Let me pull it up. Assignment 3, 4B. Okay, so it's got a
HBr and then a big ball.
Oh, I think I have a different assignment. This isn't the graded assignment. This was my assignments.
Oh yeah. Sorry, my bad.
Yeah. Are you sure it's 4B? Because for 4B, I've got.
I'll just.
Or C?
Maybe it's 5. No, I don't think it's 5.
No, 5.
Oh, it's 3. My bad. 1 sec. Sorry.
I can share my screen.
I just posted it.
Like this is assignment 3?
I just posted it. It's assignment 3. Yeah, I think you're on assignment 2.
It says assignment 3. Okay.
That's the alkene one.
I'm going to stop sharing and I'm going to jump to your chat. Yeah, that was the same. That was the same one. Okay.
Oh.
C or B?
It was B.
So B is
The HBr and then the big ball.
Oh, it might have been my answer. Okay. Oh, I'm not looking at the answer. I'm just looking at the question. Okay, it's that question, right?
Yeah, I was just wondering, so since there's a double bond on the second carbon, I'm just wondering if you're able to kind of shift that one over one and then get rid of the water and then put the double bond on the end as Hoffman, because there's a Hoffman base. I'm just wondering. I didn't really see that in the answer key.
So I think what we did was well, I'm going to just pull up my answer key because maybe it's a Hoffman base, but it's kind of under. I think there's acid. Where's my fucking answer key? Assignment 3 solutions redux. There we go. So I used so what I suggested doing was using a Zaitsev base, isopropanol, and H+.
I think it's a big ball, is it not?
Not what I have in my answer key. I think A has got that. With the potassium.
Sorry, that's what I put down. That's what I thought it was.
Okay, I think you'd still be okay. I think what you just need to be a little bit careful with is the HBr in that condition, because I think that could lead to addition instead of elimination. So what I recommended using was isopropanol and acid, because this would protonate.
Sorry, I can't see your screen.
Oh, it's not. Am I not sharing my screen?
No.
It's saying I'm sharing my screen. Okay, that's not helpful. Give me a second. Maybe oh, you know what? I think I overrode myself and I said share this other screen. And so it did that, and then oh, come on. Oh, now it's in tablet mode. I don't want it to be in tablet mode. Stop it. Sorry, you know what? One of these days I am going to learn how to use this computer. It's not going to be today. It's a Microsoft Surface. I do not recommend them. Okay, can you see my screen now?
Yes.
Yes. Okay, let's go back to. If I press that button, I can get back to here. Great. Okay. I'm just going to draw on this slide. Okay, so I recommended using isopropanol and H+. And the reason I recommended that is that if you used a Hoffman base, like a big ball, I think your risk, and I'll show you why I don't love the idea of HBr plus yours.
Because is H+ something that I would be able to use, because it's not really like definitive, you know?
Right, no, that's fair. So I think maybe H2SO4 is a great choice.
Okay.
The problem with things like HCl or HBr is you're left with Br minus and Cl minus, and those are decent nucleophiles. Whereas sulfuric acid minus is rock steady, and yes, actually it can add as a nucleophile, and you do see that occasionally, but if there's anything else, it has to be neat with nothing else present, and it's weird, and we haven't talked about that much in this class. I don't want to because it's stupid, and it never happens. So we have that's not a resonance structure, that is a forward structure. Then we have the resonance of this. So the problem I've got with using the HBr is that I think you would now have Br minus quite often coming in here.
I see.
Whereas if we don't have that, if we don't have a good nucleophile, we have something like this, which is, you know, a moderately sized ball. It's not a good nucleophile because it's too big. So it's going to more act like a base. And it's very easy to always put two double bonds in conjugation with each other. Like in cases where a substitution or elimination are kind of on the edge, like they're already always competing with each other at the best of times. But when you have another double bond present, the elimination just gets triggered into overdrive because now the product has resonance. And so the product is very stable. And so it's ridiculously stable product because it's got a resonance structure. And so that double bond is much easier to form. It's like super substituted double bonds. Like we want to have the most substituted double bond because of hyperconjugation. In this case, conjugation is even better than hyper. That's why I don't like hyper. I wish it was called hypoconjugation. It's not as good as conjugation. Conjugation is even better. So if the double bonds can be in resonance with each other, they're stupid stable. And so it's really easy to make two double bonds in resonance with each other.
See, the way that I thought of this was that I was going to use acid as a source of H+ so that water can leave.
Yeah, perfect.
You'd shift the bond over so that you have room for the Hoffman base. So like, yeah, like you'd shift the double bond on the top and then you'd have your positive charge on the very last carbon.
On this carbon?
Yeah, that's what I meant.
Well, that's what that looks like. So where's your double bond moving?
You want it to go to the next carbon on the right.
But that's going to kick out an H- if I try and draw that. Because then this carbon will be making 5 bonds.
Right.
So so if I move the double bond over there, something has to give. And so you could lose that, but that will be H-, and that's not very easy to do.
Okay, then I guess I don't really understand the question then.
So I think what I'm looking for as an answer is you can generate this, and this is in resonance with that. And then you can use your base to remove an H+.
So would it be more of a Zaitsev base
Exactly.
instead of a Hoffman?
Exactly.
Okay.
That's
because I thought it was going to be a Hoffman because you're making a double bond on the end.
Well, you're making a double bond on the end because once you generate the carbocation is in resonance with the secondary carbocation.
Right.
And a primary carbocation and a secondary carbocation in resonance, most of the positive charge is going to be on the secondary carbocation.
Right.
And so now that's available for this elimination.
Okay. Yeah, that makes sense. Okay.
But you're if you didn't have the HBr, if you actually had like sulfuric acid and a Hoffman, because if you use the big bulky terbutanol, like 3 carbons in a cross thingy, right?
Yep.
You would actually get the same product. It's going to be slower because it's much bulkier than the isopropanol I'm using.
Mm-hmm.
And if you didn't have a good nucleophile like present like Br, you would get that product. But the mechanism, the arrows would be the same as what I'm drawing here.
Okay.
It would just take longer because your cat is fatter than my cat.
Got it.
And that door is pretty skinny because it's a tertiary.
Okay. Yeah, I just mixed up the double bonds then. Okay, and I have one more question. So when you're making an epoxide, so there's one question in assignment 4 where you had like a triple bond and then you would make an epoxide and then make another epoxide because there was like unlimited HBr or whatever. So I'm just wondering.
Epoxides or HBRs? Like bromoniums.
Sorry, BR2.
Right.
That's what I meant, not HBr.
Yeah. Yeah.
So I'm just wondering, like, I don't know, this might be a dumb question, but I put the BRs on opposite sides of the bond. Is that not correct?
That's absolutely correct. Yes. So
Okay.
You will get, the first thing you'll make is that.
Hold on 1 second. Because I don't know if I did that.
Accept them on the same side, but you get them on opposite sides.
Well, you're gonna have, okay.
So the first 2 should be trans to each other.
Because at the end they had all 4 BR groups on the same side?
Well, we haven't drawn stereochemistry, but they're not all on the same side. It's just that there's two of the same thing on an atom. It's not a stereocenter.
Okay, yeah.
Right? So I don't need to draw up, down. Like I can draw up, down, but if I switch those up and downs, it's the same thing.
Okay, yeah, I'm just wondering, like, without indicating the stereochemistry, would it be incorrect to put them on opposite sides?
Well, I think you just need to be careful how you're drawing. So what I want to indicate is drawing like this is not ideal, because if you're drawing two bonds in a, that's okay. Actually, if you don't indicate wedges, but preferably we're trying to keep an eye on like the idea that things are tetrahedrons.
Mm-hmm.
So like a tetrahedron is that. So if you have two bonds in a plane, the up and down need to be on sort of the outside of this vertex.
Okay.
Right? Like I can't, this is not a tetrahedron.
Got it. Okay.
You can't get that view. That view doesn't exist.
Okay. Yeah, I got everything right except for that, and I was just wondering.
Yeah, so this is an incorrect way to draw a tetrahedron. This is good. This is fine because there's no stereochemistry, so fuck it, draw them wherever you like. But if you're drawing three-dimensionality, then what you're saying is I am drawing a two-dimensional representation of a three-dimensional object. And this is kind of like if I was drawing pictures of faces and the nose was going into the face instead of out of the face. It's like noses come out of the face. It's just the way that noses work. It would be incorrect to draw a human face and say the nose is going into the face and say, yeah, it's a fine human.
Okay. And then I had one last question. I just wanted to confirm exactly what centers, like a tertiary, a secondary, or a primary, does E1 favor and does E2 favor? Because I'm confused.
Okay, E1 needs tertiary.
E1 needs tertiary. Okay.
Ideally tertiary. It can live with secondary in when nothing else is really possible. So, but E1 wants tertiary. It can live with secondary. E1 loves resonance. Right?
Okay.
You need a stable carbocation. E2 doesn't care about where the leaving group is. E2 cares about where the proton on the carbon next to the leaving group is.
Right.
So E2s like tertiary leaving groups because because you're automatically going to have a highly substituted double bond. If you have a tertiary leaving group, you're going to have one of your carbons is going to be attached to two carbons on your double bond. So what I mean by that,
yeah, you'll have a bunch of different options for anti-periplanar.
Right. Well, what I mean, I guess more if we think about this, no matter what, if I can have that, no matter which of these I eliminate from, this double bond is going to have three carbons attached to it. And that's why E2s like tertiary leaving groups, because they make stable double bonds, because I keep pressing the wrong thing. This carbon has two carbons attached to it, so this carbon will have two carbons attached to it, and the best double bonds have the most carbons attached to them.
Got it. Okay.
But
yeah, that makes sense.
An E2 can live with a primary leaving group. It doesn't care, because all the E2 is interested in is these hydrogens, right? It wants to be able to make them anti-periplanar to the bromine. It doesn't care if the bromine is primary, tertiary, or secondary that much.
Okay. Okay.
SN2s care a lot about that because they need to attack the carbon itself.
Right.
But in an elimination, you're attacking hydrogens on the carbon adjacent to the carbon itself.
Right. Okay. Okay. I think that is all I needed. Thank you.
Okay. So Jeanette said, quick question, how does up to 5 bonus marks on a SciComm work? One of my GAs is going to look through, often we do two, they pair up. They all look through every single one of the SciComm assignments. They decide, yeah, we will, Madison, you asked that, so I will go over that. They'll go over all the SciComm assignments and they'll pull out the best 40 or 50 that they think are the best ones. And then what we do is we sit down as a panel of all the GAs and me, and we vote. And we sort of go, okay, we think this one is the best. And the top 20 or so will get bonus marks based on kind of a distribution from +5 down to, you know, +1. The reason we do this is because what we're looking for here is you can get full marks on this for about 2 hours worth of work. But there will be students who will be putting in like 100 hours worth of work on their SciComm assignment. And I want to differentiate a student who put in 2 hours of work versus 100 hours of work. And you know, it's not going to make or break a grade. I think, for example, last year, the student who scored the highest grade on a SciComm assignment failed the course, but they got their +5%. It didn't help them, but they really, really brought it for the SciComm assignment. And all you could think of is, dude, I wish you had spent 10% of this effort on studying for the midterm and final, and you would have been fine. But they were a musician. They did some completely original work, shot a music video, wrote songs, got some accompaniment doing. Other people did like big interpretive dances with their dance crew. It was some of these are just thinking, man, it's just so much work. I need to reward the effort in, because that's a ridiculous amount of effort. So we're trying to reward effort, whereas, you know, but at the same time, we're not raising the bar, so I don't want to raise the bar so high that to get the full marks you basically need to, you know, do something crazy. So it's about trying to balance that, and so that's why we're throwing in bonus marks on it instead of making it really hard to get 100. So making it easier to get 100 and then providing some bonus marks for the top ones. Okay.
Dr. Trant?
Yeah.
Quick question. For the Alyssa was asking a question about when we added like BR2.
Yeah.
Can you go back to that slide? I was just wondering, what mechanism is that? Like the trans.
It's an addition to a double bond, and it's just gonna be addition to a triple bond. Like when we add the bromine to a double bond, it's because this pi orbital of the double bond is interacting with the sigma star, the antibonding orbital of the bromine-bromine bond. And so this kind of forms this, you form this triangle.
Mm-hmm.
So it's not an SN1, SN2, E1, or E2. It's none of those. It's an addition. It's an addition 3 center 2 electron is what it's called. That's not a particularly helpful name, but there's 3 atoms, 2 electrons share between those 3 atoms. Yes, I don't know if that answers your question at all.
No, I think I just forgot to consider the triangle because I was trying to, I think, do it like really quickly in my head. So I saw BR plus, BR minus, and then I was confused with why it was trans, like why couldn't it be cis? But now it makes sense with the triangle that it'll come the opposite way.
Yeah, there we go. Because and whether it's a double bond or a triple bond, it's still the antibonding orbitals are back here, and that's what the other Br minus is going to interact with.
Mm-hmm.
So it's going to be opposite the other bromine. It's kind of now doing an SN2 on those carbons.
Okay.
To displace.
Okay.
Yeah. Okay, cool. Okay. Madison. Let's talk substitutions. So if I'm just looking at SN1 versus SN2, not considering the eliminations. So SN1s like stable carbocations. That is what they're interested in. Good leaving group. So tertiary or resonance stabilized can both work. You want to avoid basic conditions, not because basic conditions are bad for SN1 E1s, but because basic conditions favor SN2s. So the SN2s become fast when you're basic. Basic conditions don't slow down carbocation formation. They just speed up nucleophilic attack. You want it warm. So 0 degrees is normally a bad sign. Like low temperatures are normally a bad sign that you're going to do a carbocation formation. And you want a good leaving group because the leaving group needs to leave on its own. And so if the leaving group's not really good, it's not leaving. SN2s can put up with a slightly worse leaving group if the nucleophile is really strong. So in an SN2, you need an accessible leaving group. So primary is better than secondary is infinitely better than tertiary. Tertiaries are basically impossible. Then, you know, the resonance stabilized thing doesn't really matter. It weakens, it makes leaving group better if a carbocation there would be resonance stabilized, but it doesn't really make the SN2 better. It just makes the leaving group better, which probably helps everything. Basic conditions. Why? Because this leads to strong nucleophiles. Why? Because most nucleophiles are bases. Like a nucleophile is, a base is just a nucleophile that attacks a hydrogen. So reactive things, strong nucleophile, and a nucleophile matters for the SN2. It does not matter for the SN1. The SN1, you have a carbocation. The weakest nucleophile in the world can satisfy a carbocation and neutralize it. For an SN2, you need the nucleophile to kick out the leaving group. So it needs to be a strong nucleophile. Then often aprotic solvents. Why aprotic solvents? Because protic solvents can form hydrogen bonds with your nucleophile. And so they stabilize your nucleophile so your nucleophile is happy. And a happy nucleophile is not a reactive nucleophile. You want an unhappy, pissed off nucleophile. And you get an unhappy, pissed off nucleophile by having it not stabilized. And so aprotic solvents don't stabilize it very well. So those are your good solvents for that. And then often colder because it disfavors SN1. Not because it favors SN2. Hotter is always better for every reaction, but the SN1 will get better faster as you get hotter than the SN2 will. So the SN1 will become competitive as you get hot, whereas an SN2 wouldn't. When I'm comparing these two, they meet at secondary carbocations. So secondary carbocations, no resonance. That's when you run into these two mechanisms, bumping heads. Ow, that hurt. Styluses are hard. And they prove the point. That's when you have to sort of compare all of the factors, and that's when it gets really tricky. And that's when you're looking for, okay, is my solvent aprotic? What's my temperature like? Is my thingy very, very nucleophilic or not? And that's where we're looking for more competition. So if you have neutralish conditions, secondary nucleophiles, secondary leaving groups, that's when you can sort of get both reactions potentially occurring. Protic solvents are good for SN1s because SN1s, you want to stabilize the carbocation as formed. The problem if you use a protic solvent for an SN1 is you better like that as your nucleophile. Because if you have a protic solvent, you're doing an SN1, there's so much solvent and it's protic, that's your nucleophile. It's fun that you think it's going to be something else. It's not. It's the solvent that's going to be your nucleophile. So if you want to displace and have methanol as your nucleophile, great. Use methanol as a protic solvent because methanol will stabilize the leaving group as it leaves because the hydrogen bonds it. That's great. It stabilizes the carbocation as it forms. because it's going to bond to that for electrostatic interactions, because you really want to stabilize that C+. But it's then going to make a bond with the C+. So Protic solvents favor SN1s. That kind of what you wanted, Madison? Okay. I think I posted them in. I don't think I posted them in this lecture series. I think they are on the online one. So the common, let's say protic solvent is anything where you have an XH bond or X equals oxygen, sulfur, nitrogen. So methanol, water, ammonia, thiobenzene, I don't know, ethanol. Whereas aprotic solvents, the most common ones we're going to see are DMSO. We butchered that. DMF, which is THF, which is a 5-member ring, and I just drew more than 5-member rings. Those are probably our big 3, and as well as there's a whole bunch more, but I think I'll be sticking with those 3 for this course. Because there's reasons why each one of those might not be appropriate for a given reaction, but between those 3, on paper, everything works. So I'm not trying to make this harder than it needs to be. It's hard enough. You're welcome. Megan, I think your hand is up next. It actually gives me ranking. No, Melitza got her hand up first. Or maybe Melitza never put her hand down. Either way.
If Megan only has one question, she can go, because I have multiple, so.
I don't have a lot of time left, so I'll let Megan go, though, because you've already had a turn.
Yeah.
Okay, it was for a problem you did for in lecture 31.
Uh-huh.
It was
I smile and
polymerization.
nod that I know what you're talking about.
Polymerization in the presence of an alpha hydrogen.
Okay.
It kind of goes in hand with what you were doing earlier, but I'm just confused because hydrogens are not usually like drawn in. So how do I know that that's the bond that I have to break?
You have to think about the presence of those. So they're not drawn in, but you know they're there, is I think where I'm having to go with this. So you're saying I'm not normally drawn in. Yeah, but we started the course with sort of talking about sort of the assumptions of them there. So you need to be aware that they're there.
There's a double bond. So why aren't we using that to make the radical?
Why aren't we using that?
Yeah.
For the same kind of reason we just saw today. Like the initial radical, it was kind of like a failed polymerization. I think it was the example I was doing, right? Like it just kind of stopped at 2 because it kind of quenched itself.
Because in this example, there's just AIBN and heat, so.
Yeah, so I think if we have this, so so we generate the AIBN radical. Like let's just grab this example, okay? I don't know if this was what I had, but it's close enough. So it's a kind of a little bit of a hindered radical. And like I can just tell you what happens. So if it was a smaller radical, if this was HBr and that kind of thing, then we would start reacting with this double bond. And if it's this kind of free radical halogenation that we were talking about today with the light and not heat, then we'd be definitely stripping with this. This guy is a little bit on the fence. One of the problems with it, though, is that it's so big, it doesn't do nucleophilic radical chemistry. I think I have to substitute this a little bit more, otherwise the question makes no sense because all the products are the same. And again, we can make the more stable double bond by leaving the double bond there and not doing the resonance. And if this is looking around for something to react with, well, again, it's likely to do the same chemistry, that hydrogen bond abstraction we just did. The problem is that's not productive. You get the same thing on the left and right side of the arrow, so no reaction.
Like, I'm not, like, how do I tell that this is the type of question where I do it this way?
Instead of attacking the double bond with this.
Right.
This is bulky. The double bonds really only get really attacked by like HBr halogen things. In every other case, it does tend to avoid them. If there is an allylic hydrogen, the allylic hydrogen tends to be more reactive in every case, except the specific case of the anti-Markovnikov addition of halogen halides, hydrogen halides. So it's more that working with the double bond instead of this is kind of an exception. So that's why you'll note that almost all the common polymers that we see in our lives, all of our polymers are double bonds attached to things without hydrogens, like acrylonitrile, vinyl chloride, polyethylene. These are all using double bonds that don't have hydrogens adjacent to it, so the only thing to react with is a double bond. There is no hydrogen on an adjacent carbon.
I think what I'm also confused with is that today in class we said that, oh, look out for the hydrogen when you have a light or heat with a or I guess heterohalide compound or dihalide. But here there's none of that, but we still looked at the hydrogen.
Right. I think it's because this is probably more my own biases, where I think a lot about using radical reactions to do an anti-Markovnikov addition of hydrogen halides. And so I think I bias my teaching towards, hey, attack the double bond, when I should bias my teaching towards, hey, attack the allylic hydrogen. And the ones with the attacking double bond directly are kind of the unusual cases. I promise not to give you this kind of question with this kind of polymerization on the exam. I think I did say that. If there's going to be a polymerization question, it's going to involve something with no alpha hydrogens, so you can't possibly fuck it up.
Okay, I also had another question from the carbonyl assignment.
Yeah.
It was question 1L.
1L on the carbonyl assignment. That's the new one.
After this, I'll share my screen so we can go over mine.
Okay, I got a little bit of time left, so it's good. 1L, so one equivalent of lithium, of ethyl lithium, right?
Right, I know how to solve it. I just had a quick question about it.
Yeah.
So I see that we have one equivalent. I was just wondering why we didn't attack the, why we chose the ester and not, the ketone and not the ester.
Okay, so you say you know how to solve it, but then you ask me the primary question over what the question's asking.
I can see you. Okay, so
Okay, so I'm going to turn the question back on you and say, why do we attack the ketone and not the ester? What's the difference? So we agree that this is a nucleophile, right?
Yes.
Okay, so what is a nucleophile looking for?
Or the electrophile?
Right. So what makes is it going to look for any electrophile or probably the most reactive electrophile?
Most reactive.
Okay, what makes a reactive electrophile? Really simply, just the real simple answer for what makes a good nucleophile? What charge do we want it to be for nucleophile?
Charge.
Sorry?
A negative charge.
Perfect. So do we want it to be a happy negative charge or a desperately unhappy negative charge?
A happy one.
No, happy is stable.
Oh, right, right.
I want
right.
the nucleophile to be reactive, right? Okay. So the more negative charge, the better the nucleophile, right? Okay, let's turn it around for the electrophile.
Okay.
Do you want the electrophile to be more positive or less positive? To be a better electrophile?
More positive.
Right, because more positive will be more reactive, right?
Right.
Okay. Now, what is more positive? A carbon attached to a ketone or a carbon attached to an ester? How and okay, so maybe we can think, I don't know how to answer that question, they're both neutral, is a perfectly reasonable response. So let's just think about the resonance on both of these. So if you have a ketone, that's your resonance structure, right? Are we good, Meg? Oh, you're muted, Megan. I'm not sure if you meant to be.
Oh, sorry. Yeah.
Yeah? Okay. So we're good there, right?
Yes.
Okay. So if any positive charge so this oxygen stabilizes the negative charge X amount because it's an oxygen, and that's going to generate X positive charge on that carbon, right?
Mm-hmm.
Okay, so let's take a look at an ester. Okay, so we have the same first resonance chart, but is that the only resonance I've got?
No.
Right?
Right.
Okay, so if this oxygen stabilizes negative, it's similar to an oxygen's an oxygen. They're all oxygens are the same. The stabilizing negative charge about the same amount, let's say. Okay? Let's say this is minus 0.05 full electrons. Okay? Where that means there must be plus 0.05 lack of electrons on the combined positive sites. Where do you think my positive charge is more localized in the ester? Is it more localized on the carbon or on the oxygen?
I think the oxygen, because
Perfect.
it has full octet.
Perfect. Fuck yeah. Okay. So you got quite a lot of positive charge on here. Now is ethyl lithium coming in, minus charge?
Oh, okay. I see.
It goes like, yeah, I can't do anything with that. So I'm going to go for this carbon, but the carbon is not that positive.
Right.
Whereas this carbon is positive.
Yeah, that makes sense.
That's why we attack the ketone. It's a more polarized bond because of this. Cool.
Okay. Do you mind if I ask you one last question?
Sure.
And it was the same assignment, but question N. I was just looking at
the evil question.
I was looking at the answer key, and the question says 2 equivalent, but aren't you using 3?
No, because this is where we have to think about what equivalence means. So it means that for every mole, every 10 to the 23 molecules of the first thing, we've got 2 times 10 to the 23 molecules of ethyl lithium, right? So we both agree, after this just discussion we had here, that the first equivalent is going to attack the ketone, right?
Yep.
Okay. Now, this let's say it goes to completion. So we're 100% of our molecule is now this, right? There's no more ketone left. 100% of it's like this. And
right.
We still have 1 equivalent left of ethyl lithium, right?
Mm-hmm.
Okay. Now, the first molecule of this equivalent attacks the ester. Because we're out of ketones, so I guess I'll use an ester because I got nothing better to do. It's going to make a ketone out of that ester, right?
Right.
Okay. I've just made a ketone. Now, what's more reactive, this ester or this ketone that I've just made?
The ketone.
Right. So one molecule attacks the ketone, attacks the ester to make the ketone. A second molecule looks at its option and goes, I can attack the ester, but no, I'm going to attack the ketone. So the second molecule attacks the ketone again and takes it down to the alcohol. So you took one molecule of this, we went from 100 to 99%, let's say, right? Let's say we use up 1% of this. We went from 100% of lithium to 98% of that because we made 1% of this. We needed 2% of this to go from here to here. And so if I can keep dropping this, so, I do another molecule of this, let's say there's only 100 molecules, now there's 98 left, but I've used 4 of these. If I take this down to 60, I will have used 40 of these, but I'll have used 80 of these. And I'll be at 40 of this. If I have 60% of this left, I'll only have 20% of the ethyl lithium left, and I'll have made 40% of this. And then when I run out of ethyl lithium, this will be down to 50%, and this will be at 50%. And it's because the product is more reactive than the starting material. So the first, so what you can think of is for that second equivalent of ethyl lithium, half of it reacts with the ester, half of it reacts with the ketone that is made after the attack on the ester.
But
So
how come
50% of this ester and 50% of this alcohol?
I don't get how there is 50% of the ester left. Aren't you reacting it all the way to the ketone?
Well, yes, but what you're saying is, okay, now I have to react all the molecules to the ketone, and all the ketones react to the alcohol. But that's not how this works. One molecule becomes a ketone, and then as soon as it becomes a ketone, it reacts to the alcohol. But now I've just used 2 molecules of ethyl lithium to do that. But I only have one equivalent of each of these. I have one equivalent of ester, one equivalent of ethyl lithium left. But I just need to use 2 molecules of ethyl lithium to react with 1 molecule of ester. So I'm going to run out of my ethyl lithium when I still have 50% of my ester left. Because I need to use I use this twice as fast. Like, let's say I'm making a sandwich and I have 100 pieces of bread and I have 100 slices of ham. And I make really lame sandwiches. So I take a piece of ham and I stick it between my bread. And that's my sandwich is 2 pieces of bread and a slice of ham. So I make my first sandwich. I start with 100 pieces of bread and 100 pieces of ham, but now I've only got 98 pieces of bread, but I still have 99 pieces of ham. I make my second sandwich, I've got 96 pieces of bread, 98 pieces of ham. I make my 25th sandwich. I've used up 50 pieces of bread, but only 25 pieces of ham. And by the time I make my 50th sandwich, I've used all 100 slices of bread, but I've only used 50 slices of my ham. And I still have 50 slices of ham standing in front of me. And so, which isn't a big problem because ham is good, but this is why we have 50 pieces of ester still left. We use twice as much ethyl lithium to react with every ester. We needed 2 of them to react with every ester to take it down to the alcohol. And once one molecule of ester reacts to become the ketone reacts faster than the original ester. So the ketone keeps reacting. So it's not like we need to move everything forward 1 step at once. They don't move in lockstep. Every molecule reacts differently at a different time point. And so that needs to be considered. It's really easy when we draw mechanisms. It's sort of like all the molecules are moving together, but they're not. Every one of the molecules is moving at a different time. Like if you're following a reaction along, like if you're in for the in-person labs, you ran TLCs on your reactions. And after a certain amount of time, some of it had converted, but some of it hadn't. because that's how it happens. Like some molecules go first, some stick around, and eventually all the molecules will convert, or enough, almost all of them will convert. But it does take time for that to happen. I don't know if that made any sense.
I don't know if I can help, but basically, like, as one molecule is made, it's reacting with the lithium ethyl, and then, like, by the time that, like, you create the final product, like, half of it's reacted already, so there's not half of it left to convert the initial thing, if that makes sense. Like, the reaction, it doesn't take the first thing, make the second thing, and then it's going to create all the third thing. It's as the first is made into the second is being made into the third.
Yes.
I feel like this is a simple question, but I just can't wrap my head around it. Okay, so to take the ester from the ester to the ketone, that takes one equivalent, but then from the ketone to the alcohol, that takes half.
No, it takes another equivalent. You still need another ethyl lithium. So ester to ketone takes one equivalent of ethyl lithium. Ketone to alcohol takes another equivalent of ethyl lithium. But, so if you had 3 equivalents, like in M, which is the one above, the answer is it all becomes the alcohol. But you only have 2 equivalents. So you only have 100 esters and 100 ethyl lithiums at this point. One ester reacts to become the ketone, so you have 99 esters left, and you have 99 ethyl lithiums left because you used one. Then the one that just became a ketone, the ethyl lithium looks at its options and thinks, I can attack a ketone or I can attack an ester. I am attacking a ketone. You just made a ketone, so it attacks the ketone. Now you used 2 ethyl lithiums, but only 1 ester, and you made some alcohol, and you have no ketone left. As soon as the ketone is formed, the ketone becomes the alcohol.
Okay.
But you're using the ethyl lithium twice as fast as you're using the ester.
Okay, got it.
And so you run out of ethyl lithium when you get through half the ester, and then you're out of ethyl lithium. And so you're sitting there holding your ham. Yeah, I actually thought my sandwich analogy was pretty good. It clearly didn't work, and I'm a little disappointed by that. But that's okay. I will get over this.
Thank you.
Can I ask my questions now?
Yeah, I can take one more question. Sorry.
That's okay.
It's a quickie, Melitza.
Okay, I'm just.
Megan, I do really appreciate you sending me those questions ahead of time. That was awesome. Thank you. Oh God, there's a video of me. That's awful. You're muted, eh?
Okay,
nice.
There we go.
Okay, now you stop sharing your screen.
Yeah, I'm gonna start it again. Okay. So, okay, I just have to figure out what I'm gonna ask because, okay, I'll start here. Okay, so right here, how do I know what the Br plus is going to attack? Like, how do I know that, like, where is it gonna attack here?
Like if it's gonna be up or down?
Yeah. Or no, not really up or down, but is it gonna attack here or here? Because to create this product, it has to attack here.
I think what okay, so I would have accepted either answer. Like, so that's why I gave the product there and I didn't ask you to draw the product, right? Because the answer comes down to it does a diaxial ring opening, and we haven't talked about that. So you can't. Those are identical as far as you're concerned. And I think if you had actually answered the opposite and attacked the other carbon instead to avoid the up methyl group, and you said, look, I'm avoiding the up methyl group because the other one's closer, it's going to be worse, I would have given you full marks for that argument.
Oh yeah, I just didn't know like whether it attacked this one or this one because they were both secondary.
Yeah, you can't tell, and there's no real induction effects. There's, from what you know, you cannot differentiate.
And also, would it be secondary or tertiary? Because we learned about the whole halide thing.
I would still call them secondary carbons, but in terms of hyperconjugation stability of a carbocation on that center that bromine is attached, it would act kind of like a tertiary, but it's still a secondary carbon. Yeah, carbon status is all about how many carbons are attached.
Okay.
But that's not the only thing that matters for hyperconjugation. So it's like, does it even matter?
Yeah, I think that was the
I don't
same
know.
thing.
I'm using the nomenclature as it is and sharing the ambiguities, and I'm sorry. Okay.
Yeah, I think that was the same thing here too, because I didn't know like how to get it to attack here, because they're the same.
Yeah, so I think you can just kind of go, I'm hoping for the best here. So what I was actually looking for here was a radical reaction. Because that hydrogen at that other carbon.
Here?
Nope, the other at the tertiary carbon.
Oh, here?
Right, that's going to make the most stable radical. If you use a radical source, you can add a Br to that thing doing free radical bromination or free radical chlorination. If you had Cl2 and light, you would add a chlorine there, you keep the double bond.
Okay.
So you could put the chlorine on that center.
Like
then you
here?
could reduce, yeah, right? Then you could reduce the double bond using hydrogen and palladium. And then you could do a Hoffman elimination.
How would you add the
chlorine and light. The radical chlorine reaction that we saw.
Wouldn't this attack the chlorine? Or
nope,
no?
Because you form a more stable radical, which is the allylic radical, not the double bond reacting. Just chlorine and light, as we just did in class today.
Okay, I'm gonna write that down
Review
and
that.
think about it later.
Okay.
And also.
But I would give you most of the marks for this because everything else you're doing is correct. What I would do is I would sort of say, on your second structure, I'd say separate from the other molecule because you'd get the other bromine too, as you pointed out. So you're going to just take the one I want and I'll do elimination.
Okay.
If you did that, so then if you said that, like separate the two molecules, I'd give you full marks on it. But I was looking for chlorine and light because it's just the way we can do that.
Okay. Okay.
I do need to run, so I'm going to cut you short there.
That's okay. I'm just gonna tell you to quickly look at my midterm mark.
Did you email me your grade or your PowerPoint?
Yeah, I'm just telling you because like I could have just left it, but I have 110% on it.
Oh, that's interesting. What should your mark be?
About
100?
I think no.
Okay.
It was supposed to be, I think, 16. Wait, 1 second. I'm just trying to figure out. I lost 0.5 and then 0.375. So did I do that right?
I'll check your midterm mark, Melissa. Somebody obviously entered a number wrong. I do appreciate. We would have caught it on when we're doing it, and it's nothing on your fault. It's all on us. Tempted to leave it as is, just like as both of you guys for like bonus participation grades, because you basically make this course worth teaching. Thank you.
I know a couple people that had this happen too, but it was just like only 2 bonus marks, so they're not going to say anything. But I feel like because it's 10 bonus marks, like it's just not fair to the other students.
Well, no, I'll go through and check. Yeah. We'll just make sure that now the grades look way over 100. Oh yeah. I hate doing these online tests so much.
Yeah.
And these online grading. I'm sorry, and we don't give you like written feedback and things because there's no quick way to sketch things on paper.
Yeah, I mean, if you want to leave it, that'd be great because then I have a better chance of getting the grade that I want, that I need for med school. But I mean,
I do appreciate it. I'll take a look. Okay.
All right. I know you have to run, so have a great rest of your day.
Bye, guys. Have a good day.
Thank you.